Hi everyone. In this video, I'm going to explain about a synchronous counter design. So, a synchronous counter design is quite different and difficult compared to asynchronous counter. So, in asynchronous counter, all the flip-flops are T flip-flops, and we don't have any logic circuit at the inputs of the flip-flops. But whereas in a synchronous counter, we should have lot of logic circuitry involved along with the flip-flops. Okay, so regarding clock pulse, all the flip-flops, we don't have any problem with the clock pulse because clock pulse is common for all the flip-flops. How many number of flip-flops you are going to use, that many flip-flops will be having a common clock pulse. Okay, that's why they are synchronous each other. So synchronous clock, synchronous counter. Okay, now let us design a 3-bit up-down counter. I'm going to design 3-bit up down counter using JK flip-flops with reset and clear pins. Okay, now up down counter, that means a single counter has to perform both the operations, up count operation as well as down count operation. So 3 bits are nothing but 000. This is the present state. Up count will be happened if suppose we have to consider one more pin along with these three. We have to consider one more pin, that is some mode. That mode pin will be 1, and then the count will be incremented like 001, and mode pin will be again 1. The count will be incremented as 010. That means if the present state is 001, if mode is equal to 1, then it will be incremented to next state. Again 011, 100. So this all happens when mode is equal to 1. Next 101, 110, 111. Okay. So this is for mode equal to 1, and this is for mode equal to 1, and again this, sorry. Okay, so this is for mode equal to 1, and again this is when mode is equal to 1. Again this will be when mode is equal to 1. Okay, this is fine. What is the reverse counting? Nothing but when mode is equal to 0, if the present state is 000, then the count will be 111. So if mode is equal to 0 like this, and this is down counting, this happens when mode is equal to 0. We are setting the mode pin like that. Okay, so we need a logic circuitry for this mode. Okay, this is what the expected counting operation. So when mode is equal to 1, up count operation should be performed, and similarly when mode is equal to 0, down count operation should be performed, down counting. Okay, so let us see the truth table, or we can say excitation tables, because in order to identify the inputs of J and K, we should consider excitation table. So present state, mode is nothing but some M, next state, and then required flip-flop inputs, nothing but JK. How many flip-flops we need? What is the count? 000 to 111. So 3 flip-flops we need. 3 flip-flops means each flip-flop will be having 2 inputs. So total 6 inputs we need. So J3, K3, J2, K2, J1, K1. and the present state Q3, Q2, Q1. Mode is nothing but M. Next state again Q3, Q2, Q1. Okay, this is the excitation table. In excitation table, we should consider present state, next state, and required inputs. Already we have done in the design of conversions of flip-flops. Okay, now we have to consider mode pin is also one of the inputs of the present state. Okay, so that means count will vary from 4 zeros to 4 ones. So 000, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 111. Okay, we'll continue it in the next slide. Now, when mode is equal to 0, is it down counting or up counting? Down counting. So, what is the down count for 000? Down count is 111. Again, for the same 000, when mode is equal to 1, up count, nothing but 001. For 001, it is down count, so 000. Again, this is 001. Again, here 010. All these are down counts. And coming to up count, this is 1 means 2. 010 here, 2 means 3, 011. And here 3 means 4, 100. 100. And similarly, Q3, Q2, Q1, M, Q3, Q2, Q1, J3, K3, J2, K2, J1, K1. Okay, so 1 000, 1 0 0 1, 0 1 0, 0 1 1, 1 1 0 0, 0 1 1 0 1 1. Okay, and when it is 0, down count, it is 3, again 4, here 5, 6, and for 4 it is up count 5, 101, 5, 6, and for 6 it is 7, and for 7 it is zeros. Okay, now our next task is very important. We need to identify the excitation table of the JK flip-flop. Excitation table of JK flip-flop already we have seen. Okay, so we need to consider the present state and next state, and then we have to identify what could be the inputs of that one. So for J3 and K3, we have to consider Q3 and this Q3. Otherwise, you can say next state Q3 plus. That is better to pronounce. So Q3 and Q3 plus. Present state is 0, next state is 1. Present state is 0, next state is 1. Then J3, K3 will be 1x. And present state is 0, next state is 1. Same here also 1x, here also 1x. Next, coming to present state is 0 and next state is 0. That is 0x. Okay, I am taking all these required flip-flop inputs. Okay, if you have any doubt, you can take that excitation table and compare. Up to 100, it is 1x, 0x, 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 and here it is 0x, 0x, 1x, x1, x0, x0, and it is x1. Again 1x, x1, x1, 1x, 1x. Again x1, x1. And coming to the next state, x1, x0s, last x1 again. So all these we have derived from the excitation table of the JK flip-flop with the present and next states. 1x, 1x, 0x, 0x, 1x, x1, x0, x0, x1, and the last column 1x, again 2, 2, 2. Okay. Now what we need to do, we need to identify the equation for J3, K3, J2, K2, J1, K1. So for that what we need to do, we should use 4 variable K map for writing the Boolean expressions for J3, K3, J2, K2, J1 and K1. J1 and K1. Okay, so I am taking all the expressions directly because that will be taking lot of time. Taking the 4 variable K map, okay, mapping them and just finding the common values, common product terms. You can also do it. Okay, so that we have done for multiple times. J3. Now the expression for J3 is the simplified Boolean expression for J3 is Q2 bar, Q1 bar, M bar plus Q2, Q1, M, and J2 is equal to Q1 bar, M bar plus Q1, M, and K3 is equal to Q2 bar, Q1 bar, M bar plus Q2, Q1, M, and K2 is equal to Q1 bar, M plus Q1, M, Q1 bar, M bar plus Q1, M. And what about J1 and K1? J1 and K1, if you go to the truth table, excitation table, see J1 will be having 1 1 xx, 1 1 xx, 1 1 xx. All these will be like this. Again, K1 is also same but in reverse order. But when you map all these J1 and K1, there is no zero term in the J1 and K1. See properly. In J1 and K1, there is no zero term. There is no zero term. So that's why we can take directly a logic one because all these can be mapped in a single product term. So all the min terms in the K map can be mapped so that J1 and K1 will be 1. Yes, there is no 0 in J1 and K1 columns. All the product terms, all the min terms are mapped in K map. So J1 is equal to 1 and K1 is equal to 1. So that's why they can be shorted and given to 1. So the logic circuit diagram of this one is, so the logic circuit for this one is logic diagram for this 3-bit up down counter. See here, J1 K1 are given with logic 1 and J2 K2. This is the logic circuit what we have got the expression for the J2 and as well as K2. And another important point here is, want to see the expressions, J3 expression and K3 expression, these two are common, and similarly J3 K3 is common, and similarly J2 K2 is common. That means we can short circuit the J3 K3 and similarly J2 K2. That's what we have done here. So J2 K2 short circuited and given to the output of this OR gate, and here also J3 K3 are short circuited and given to the output of this OR gate. And these are the gates used to do that manipulation. What we have got the expression, Boolean expression. This is 3-bit up and down counter. 3-bit up and down counter. See, this is the mode pin. This is the mode pin. Mode pin which is used for the selection of either up count or down count. And one more important point is clock is common. Clock pulse is common for all the flip-flops. See, a common clock pulse is given. That's why it is synchronous counter. It is synchronous counter. Okay. Thank you.